Okay, let's get started. This early in the morning. Pleased to welcome Professor Anupam Mazumdar to our midst. He's going to be giving a couple of talks during his visit. This is number one. The next one will be Cosmo Lunch tomorrow. Highlights, excerpts from his CV, pages after pages. No, I'm not going to read it all. He's presently at the University of Groningen. Before that, he was had faculty positions at Lancaster and Nordea in Copenhagen. Very importantly, he was a CITA National Fellow long ago, it seems, at McGill, and before that at ICTP in Italy. He's been most recently a visiting fellow at the Princeton Institute for Advanced Study in JSPS in Tokyo. Long ago, but not as long ago as me, he got a PhD, and that was from Imperial College. And the title of his thesis was Early Universe Cosmology. He's worked in many different areas of theoretical physics, including classical and quantum gravity, quantum information theory, particle physics, early universe cosmology, and astrobiology. Fairly recently, in 2019, he had a report in progress in physics called Cosmic Phase Transitions, Their Applications in Experimental Signatures. But since then, or about then, he began to pivot to a new field for him, an exciting new area for international theoretical and experimental physics, and that's the title right there, Witnessing the Quantum Nature of Spacetime in the Lab. He wrote some seminal papers in 2017 and 2021 to establish this experimental protocol called the quantum gravity-induced entanglement of masses. That has been taken up by physics societies as something to do in the next decades. So his talk's not going to be decades long, but it's going to introduce something that will be with us for some time. So we're looking forward to your talk and the rest of your visit.
Thank you very much, Peter, and thanks a lot for the kind invitation. I have got fond memories of this place. First, as perhaps as a PhD student, I came in way back in 1998, and then I became a CITA National Fellow, and I visited many times in the course of my postdoc at the time. And so, yeah, it's really my privilege to be back here and to talk physics with all of you. So, okay, so today what I would do is I would talk about witnessing the quantum nature of space-time in a lab. A simple question, actually, we wanted to ask is that can space-time with matter be in two places at once? So can you create superposition, quantum spatial superposition with matter or not? And so way back in 2017, we wrote this paper with quantum information, quantum technology colleagues. Many of them are experimentalists. And in 2023, we provided an analogous experiment for light bending. The famous light bending experiment, which led to the establishment of general relativity. Can there be a quantum analog for that or not? So these are two experiments which I think will definitely help us understanding the nature of space-time. Of course, they are extremely, extremely challenging, and this is what I'll be discussing today. So, gravity is fascinating. I mean, it has attracted many many minds, all the ways. So one of the oldest interactions we have known so far since the days of Isaac Newton, or even before that. And still, the problem is that we hardly know about gravity. We know all the other interactions extremely well. We have probed them. We spent $1 billion to even dig out what Higgs stands for, what does it mean for us. But when it comes to gravity, we know very little about it. So I have added Feynman's picture. He had plays a very interesting role in this game. Hopefully we can talk later. So, as I said, the origin of space-time and gravity is still not very well known. We don't know whether space-time is classical or quantum, and that's the whole aim. Aim is to test whether can there be an experiment which can test the nature of space-time, and especially in a lab, in a tabletop experiment. So, plan of my talk. So, I will talk about very simple foundations. You will see how simple it is. It's as simple as perhaps any first-year undergrad level physics, actually, not very complicated physics. I'll talk about a little bit about what do I mean by quantum gravity at the bare bone structure level, not fancy talks. I'll talk about macroscopic quantum superposition. These are two examples I mentioned, and most of the talk perhaps will concentrate on what are the experimental challenges. So we are really, imagine ourselves being 30 years before LIGO experiment. So we are at that stage, and hopefully it will take us some 15, 20 years to build this kind of experiment. Good. Okay, so let's start with something very basic. What do I mean by classical and quantum? Because after all, this is a debate. And so here we have got a famous gentleman standing in front of Ferd Hall. In a classical physics, you would know everything. You know the color of my dress, all properties, classical properties, you can figure it out. But imagine if I had a spin, electron spin, and you have got spin x, y, z direction. So information about incompatible properties exist. I know that if there is a sigma x, there is a sigma y. But in quantum mechanics, I cannot measure them simultaneously, all of them accurately, which I can do perhaps in classical system. So this is a stark difference between classical and quantum, which we all know. Another example comes in perhaps talking about correlations, classical correlations and quantum correlations. So imagine I've got this top. The kids like to play this kind of top. So if I had a classical top, I know it's point up and point down. So I have a classical correlation. But imagine if this top, instead of this top, if it were an electron, it would have all sigma x, sigma y, sigma z. It would have all rotations, yeah. And you can build correlations with the two spin systems. So for instance, in this picture, forget the state. You don't have to pay any attention to the state, but what can happen is that you can build correlation in x direction, y direction, and z direction, which you cannot do perhaps in a classical system because you have fixed the direction and the angular momentum of this top, let's say. So these are the two differences. These are kinematical differences, if you want to highlight, in classical world and in quantum world. So in principle, you see that now if you think of these to be your states, quantum states, so from a quantum state, you can get classical correlation, but quantum system, truly quantum system, possess even larger correlations. It's different from classical correlation. So one important, as any theory, pick up any theory, doesn't really matter, classical mechanics, quantum mechanics, any field theory. You have kinematical properties of your theory, also you have some dynamical aspects of the theory. And the dynamical aspects comes in because when you talk about the interactions. And those interactions also change the correlations. And these correlations, especially for quantum system, they give you something which is bona fide to quantum system, which is entanglement. So just to give an example, this is an example of a product state. You have got two spin systems, let's say. But if they don't interact between them, this can be described by a product state, which is kind of pure state. But if you allow some interaction, you can get something which is not a product state. And these are typically known as entangled states. So this entanglement is really a bona fide quantum entity. There is no classical analogy to this entangled state. And by the way, feel free to ask me questions anytime. Okay, so I briefly introduced you this quantum gravity-induced entanglement of masses. So what QGEM does is that it entangles any two spatial superpositions. So imagine if you have got a spatial superposition here, described with delta x, and here is another spatial superposition. You can call it, for the timing, forget mass, just consider it like a spin. Like I take this object top and I create a spatial superposition stop. Spin up and spin down. This has a spin up and spin down system. I can create this spin up and spin down via this Stern-Gerlach apparatus. The Otto Stern and Gerlach's famous experiment, which is almost 102 years old now. And suppose if you create this, and if you allow interaction between these two systems, call it Alice and call it Bob, so the two spin systems will get entangled, exactly in the same way as I've shown you here. Like Alice and Bob, they will get entangled. They will have interactions. And but what entanglement requires? It requires a quantum mediator, which I will explain you below after this slide. So what do I mean by quantum mediator? So if you allow quantum interaction between them, then they will entangle. So that's the statement. And there's also a theorem I didn't know actually before. I came to know from my quantum information colleagues, and this is a very celebrated theorem, comes from quantum computing personality Bennett. He's in IBM. And there are many people actually contributed to this theorem. There are many, if you look at citations, perhaps 5,000, 6,000, more than that perhaps. So anyway, what is the statement? The statement is very simple. Let's say you have got Alice and you have got Bob. And imagine if Alice and Bob, they have their quantum systems. Maybe they have spin systems, they're doing some quantum experiment, they're observing something out of the experiments, so they got some data. But imagine if Alice and Bob, they are talking to each other via classical channel. If they're talking to each other via classical channel, the statement is that they are not going to get entangled. So A and B would never get entangled. So this is what LOCC stands for. LOCC stands for local observed operation and classical communication. So as long as you have got local operation and classical communication, then you're not going to get entangled. So on the other hand, if you have local operation and quantum communication, then you can get entangled. So that's the statement of LOCC theorem. So if you think about what is quantum gravity, it doesn't really matter how you quantize it. If you just take the bare bone, simplest definition, so this will be the simplest definition of quantum gravity. The ability to perform quantum communication, hence generating quantum entanglement in quantum systems. So you have got some space-time here, you've got space-time here. If gravity or space-time is inherently quantum, these two space-time regions would get entangled. And this is the simplest definition of quantum gravity. Nobody spells it out because it's so simple. Perhaps people have, sometimes you forget under the rug. So that's the kind of statement I'm going to play with. Why? Because you see, anything to do with gravity is extremely hard. You're talking about 36 orders of magnitude of difference between electroweak scale and the scale of Planck scale. So if life gets harder, what do? You pick up the simplest game. You don't want to play a complicated game. And this is the simplest game I'm going to play with. So it's independent of how you quantize gravity. It doesn't really matter for me. Okay. So this the experiment in 2017 of the protocol which we gave, so what we noticed is that actually gravity, if it were quantum, it would entangle two nanoparticles. So nanoparticles means mass of roughly 10 raised to minus 15, 10 raised to minus 14 kilogram, depending on the density. Density if you take the diamond, which is roughly 3.5 kilogram per cc. So roughly of that system, it would entangle if you manage to create a spatial superposition of roughly 10 micron separation. And if you can keep the system alive for roughly around a second, these two systems would entangle. And you notice that I have put a shield here, because your largest background is electromagnetic background. So you know that electromagnetic background can be shielded. Electric field can be shielded by putting a very good conductor. Magnetic field can be shielded by using Meissner effect, but gravity cannot be shielded. So this experiment, since you need to understand the biggest background, which is electromagnetic background, you can shield it. And if you can perform this experiment, and if you can, at the end of the day of the experiment, you are going to look into the correlation. You're building the correlation left Alice and Bob's end, and you are looking at how many times you're getting spin up, spin down system. And of course, if the systems get entangled, you will see that correlation is not 50-50, maybe 51-49 or something like that. So you're looking for that small difference between these two systems. And if this correlation, if you do see this correlation, which leads to entanglement, then you can ascertain that gravitational interaction between these two systems is inherently quantum. Hence, you can conclude the space-time is quantum. So this is the basic statement of the experiment. Now, in real life, of course, when you want to do the experiment, real life is hard because the experiments are never very clean. You are surrounded by this environment. So what you look at some kind of like witness. And this is the terminology which comes from essentially quantum computing, quantum information side. It's because in quantum systems, everything decoheres, or everything will dephase your system. Even a rattling snake will dephase the system. So everything, since causes trouble for you, you're looking at the witness, and you can show, other colleagues have also shown it, that what happens if you have a bipattern system, like spin-up systems like the one which I've shown you for Alice and Bob, if you can, so it's easy to differentiate between what are separable states and what are inseparable states. And this is just a mathematical definition. I mean, you can derive it. There are ways to derive this witness, but for the timing, instead of derivation, I will just focus on that if this witness W and rho is the density matrix of the system. If it's less than 0, you can say that there are entangled states. And so think of it like these are bells. In the Bell's test, there are bell correlation. So it's like, think about, this is your unitary matrix. You have got sigma x, because you're playing with the spin of system 1 and system 2, sigma y, sigma z of spin 1 and 2, and again, sigma z, sigma y of spin 1 and spin 2 systems. So the criteria is that you're looking for the trace of W times rho has to be less than 0. And rho is the density matrix. I will give you a very simple definition of that. So what you can do? So what you can do is that this is something which is a very backbone to anyone who does gravitational waves. Those who are playing with gravitational waves, they are looking into two masses, and they're looking into the potential of the Hamiltonian. They're looking into and the first term is Newtonian potential. The second term is post-Newtonian contribution. And eventually you will see even quantum corrections if you believe in just perturbative quantum gravity. You don't have to go into perturbative quantum gravity, but if you believe in that, in the simplest case, you will see this kind of terms, h bar terms will appear. But the caveat or the weakness comes here, because it's g squared suppressed. G itself is a very small number. And if it comes g squared, it's even smaller number. So, that's the level at which the h bar enters into the game, and then you can keep building it up. So if gravity is really if it were a quantum entity, then effectively all these terms would lead to entangle the two systems. So imagine, just for the sake of imagination, if you play with the two black holes, and the black holes are really quantum entity, they're actually, while encircling each other, sort of in the binary system, while they're coalescing, they're actually entangling as well through these interactions. Higher and higher order interactions will come into the game to us as close as when you form the real chirp event. So the hope is that, well, you will see that challenge even to test this first term. This itself will take us something like 15 to 20 years, and if we can manage that, maybe, I would say, maybe 100 years or so it will take to get into this level. Okay, so let's go very simple theory. There's not much of maths, but very simple. What exactly, I mean, many people have asked this question that, look, there is no h bar in Newtonian potential. Is it really classical or quantum? Because sometimes people associate that in order to see quantum, you have to have h bar somewhere. But that's actually not true. So, I mean, h bar, of course, that's one element to quantumness, if you want to say. But the other element is that what I said, that this the entanglement. Yeah. Now, very simple way to understand this would be, without going into any mathematics, if space-time is quantum, if you're really quantizing your space-time, and so this is your Minkowski space-time. The moment you have added matter, let's say that these are quantum systems, quantum harmonic oscillators, and then what will happen? You can ask this question that if you have added these two systems, quantum systems, they will change your gravitational potential, gravitational energy. Now, if gravity is quantum, the change in the gravitational energy has to be quantum. So what does quantum here means? What it means is that the position, momentum, all these are no longer C numbers, but these are operators acting on some states. So exactly like the simplest case would be the Newtonian potential, or the change in the gravitational energy will be given by the Newtonian potential, and of course there will be other terms, but now positions are now operator entities, operator valued quantities. And it's a very easy way to understand it. This is something which I teach it because I'm teaching quantum physics too now, Griffith's book essentially, and this I teach them even in my lecture. So imagine you have got two harmonic oscillators, system A and system B. And so let's imagine this, they are in number states, so they are in ground state, 0, 0. Now, suppose you add interaction, it doesn't matter, any interaction. What's going to happen? Your Hamiltonian will be now HA, HB, and this is a small perturbation. And in a perturbation theory, even in time-independent perturbation theory, you can compute how the wave function, initial wave function will evolve the final wave function. And so what you can do is that you take this final wave function and massage it a little bit. You see what I've done. I have just separated the ground state and I've added and subtracted A and B n term. So what I have done here is that I have recast this final state into something which is called product state, because these two states, these two entities are just product, or something which is non-product. And this hides the information about interaction, because if this quantity, this coefficient, which you can compute in your second order perturbation theory, if it's non-zero, it immediately tells you that the entire wave function, final wave function, is entangled. Now this interaction, HAB, could be anything. It could be QED, it could be QCD, it could be weak interaction, phonon-mediated interaction, and including gravity. If gravity were quantum, you can do this calculation. And of course, in the case of gravity, you have to be a bit more careful. Well, even for QCD, you have to be very careful, and QED, all of these interactions have to be careful, but you can compute how the final wave function looks like. And you can also compute this coefficient, and so on and so forth. So I'll just give you an example of gravity without going into the details. So this is exactly what you're computing in the second order perturbation theory, where this K is your graviton state. Now gravity, because it's a spin 2, it has the state, one particle state is slightly complicated, but forget those complications. If you know the maths, you plug it in, and actually you can derive this beautiful change in the correction to the potential energy or the correction to the energy difference. Okay? And people actually use it. I mean, there's now a huge industry, colleagues like Zwieburn, and many people actually compute in many different ways. Nimar, Kani Hamed, the people use many different techniques to compute this change in the Hamiltonian. And now I think people have gone to post-Newtonian 7 or 8, I think. I do not know what's the current state, but people have gone way up high in this Stolberg of structures. So if you take the first term for the two harmonic oscillators, they're separated by, say, distance d, delta xa and delta xb is just the Gaussian wave packet, width of the Gaussian wave packet. You can immediately see that the entanglement builds up in a Taylor expansion. Imagine that because the d is bigger than delta x. Delta x is the square root of h bar divided by m omega. Omega is your frequency of these harmonic oscillators. And you see the cross term will entangle the two systems, because you will get delta xa times delta xb. So exactly, so this is essentially the physics which will go into creating also the experiment. But in the experiment, what we have to do is that we have to create not a Gaussian state, but a non-Gaussian state. It's really specially separated, because you can compute the entanglement for the Gaussian case. Turns out to be very small, so small that you can't detect it. So you have to create this kind of non-Gaussian state. So what are the parameters? So the parameters, they don't look so bad. You see the mass of the systems, it is around 10 raised to minus 14 kilogram. Delta x is around, let's say, 100 micron, and this distance d is 500 micron. And if you keep this system alive for roughly 1 second, you can build the entanglement phase roughly order 1. Of course, these were the numbers. We wrote it in 2017 paper, and now we are improving these numbers. We are trying to see what can be done to improve some of these numbers, because 100 micron is still a big challenge for a micron size system. So far, nobody has gone to this realm at all. And this is the wave function of these two, Alice and Bob. It's like a spin system, because spin is embedded in these systems. Spin, why we play with the spin? Because the spin acts like, for me, like a ruler. Because in a quantum system, I don't have a classical ruler. I need some quantum system to figure it out. So spin systems, that's why we play with the spin system, because spins, you can read it out. Optically, they can be read out very easily in an experiment, especially for a system like diamond, because diamond has very, the lines, the transition lines are very well known from ground state to excited states. So you can read those, by shining light, you can read the spin. So spin, so I can, after the experiment, I'm doing the interference experiment here, and at the end of the day, I'll have some spin population. How many times I've got spin up, spin down, spin up, spin down, and so on and so forth. And not only spin up and spin down, I can look into sigma x, sigma y, sigma z. I can repeat the experiment, and I infer all the spin properties of my system. So these are the numbers. But as I said, that in real life, it's extremely hard. Why? Because what happens is that anything can decohere the system. And this will tell you, this will amaze you, that how much do we have to push the technology forward. So here I'm just giving you some numbers. So this is an example of your density matrix. You take wave function, the one which I showed you. Here I've taken the wave function of single system, not for two systems, but just in single system. Single system is this concentrate on this system because it's easy to explain. So in the density matrix, if these terms, the off-diagonal terms become 0, then the system will become like a classical system. But if these off-diagonal terms are non-zero, that means the system's coherence is preserved. But as I said, that even air molecule, the pressure, the temperature, everything will destroy the coherence of the system. If the system has its own impurity, that will destroy the coherence of the system. So you have to model all those things. And just to give you an example, as you increase this gamma parameter, which is called the decoherence rate, if you increase the decoherence rate to get the 99% confidence level, you need to repeat the experiment more and more. You see roughly 35,000 runs you have to give. Now imagine if you want to do the experiment in 1 second, this entire experiment if you want to finish in 1 second, it's roughly 35,000 seconds. That comes to roughly 4 or 5 months continuous run to infer something about the witness, whether it's less than 0 or not less than 0. And if you increase the experimental time, if you make it say 10 seconds or 1 minute, perhaps it will take even longer time. And so it says that how hard it is. So we have to control this parameter. We have to make it smaller and smaller. And that's the place where the challenge comes in, that how do you control the decoherence rate and minimize it so that you can do the experiment, say 5,000 or 10,000 runs. And that brings the quantum technology. So it's a multi-pronged attack. You need to maintain the quantum coherence. So everything, as I said, everything destroys the coherence of the system. So just to give an example, you have to internally cool the system. So in the case of this diamond, you have to cool it below 4 Kelvin so that you don't excite phonons. You have to put it in a vacuum, which is as good as the vacuum you have in LHC, where the 2 protons are colliding. If the vacuum is not good in LHC, the protons are not going to collide. They're just going to miss. There will be no event. So that's the level of vacuum, which is roughly 1 part in 13, 1 part in 15 Pascal level vacuum you need. You need to cool down the center of mass, because if the system is jiggling around, you're not going to even create a superposition. You have to bring it to the ground state. And some of these technologies have only recently been available. Only recently in 2000, people have managed to cool the nanoparticle silica to a ground state, in a quantum ground state. So all these things you need to maintain the quantum coherence. You need to shield it. You have to shield it from cosmic rays even. So you have to go underground. As I said, that even seismic noise, it's a 1 second experiment. 1 second means I'm sensitive to something which is happening even in the Pacific end of Canada. If there is a wave, if there is a big wave coming in there, it is going to affect my experiment. This will be a big noise for me. So I need to go underground to go for the vibration isolation, which is very similar technique which LIGO, Einstein telescope, they are going to achieve. Or LIGO has of course achieved, but we need to go to 1 Hertz kind of experiment. So I'm just showing you very simple-minded temperature, pressure, time. These are the acceleration noise, the current noise, the gradient noise. But believe me, the stable actually is way, way too long, because any fluctuation can perturb my system. So this is just simple examples. I've given you some numbers. You don't have to look into the numbers, but it requires extreme protection. That's the bottom line. So just to give an example, actually this calculation was first performed by Kip Thorne. I was just discussing in the morning with Peter, Kip Thorne and Kip Thorne's wife, because they were interested in LIGO experiment. So if a rabbit passes by, if snakes rattle, then how is it going to affect your the beams, the laser beams? So it's similar kind of calculation you need to do even for this experiment, because after all, it's an interferometer experiment. So you have to isolate the state experiment. So what it means is that just from the continuous motion, so there's an exclusion zone. We are creating some exclusion zone, something like 1,000 meters, 10 meters, some seismic, say cars, aeroplanes. So you need to create this experiment. You need to do this experiment in a very isolated environment. So for 10 raised to minus 15 nanoparticles, you see that you are actually sensitive to very, very tiny accelerations, roughly 1 part in 15 meter per second square. You are measuring it in 1 second. It's perhaps the most sensitive experiment you will ever do on Earth. We cannot afford to do it in space because You need to repeat the experiment, build statistics. If something goes wrong, then the entire experiment goes wrong. So you see that this is the current state of the art. This is I have taken from a colleague who works for Einstein Telescope and CAGRA. And right now, we don't have the technology to go to 1 hertz. Right now, Einstein Telescope is in the most advanced stage, hoping to get up to 3 hertz. And since our experiment is around 1 hertz, we have to push the R&D towards that direction. So, or we may have to push, we need to create the experiment at roughly 5 hertz or something like that. So we need to finish the experiment even at a much smaller time scale. So these are the challenges when you go into this experimental domain, but it's possible to reach the numbers. So even with CAGRA, it's possible to reach 10 raised to minus 15 meter per second square of sensitivity at around, say, 2 hertz or 1.5 hertz is possible to reach. So it's not that extremely hard, but still it requires some finance, some money to push it further towards your left. But unfortunately, you know that CAGRA is not working. It is not giving you anything. Japan has spent $1 billion, but unfortunately, there's something wrong with the vibration system. So, how much time?
Another 20 minutes till the hour.
So, as I said, that's one frontier I have discussed. The other frontier is that chip, because you see that how you're going to perform the experiment. If you touch if you touch your nanoparticle, it's going to exchange the heat. Heat transfer will destroy the coherence of the system. So you need to levitate it. You have to play at the level of vacuum. You cannot play with the electric field. Electric field intensity is much larger than the magnetic field. So if you think about the Hamiltonian for electric and magnetic field, the magnetic field Hamiltonian part of the contribution is much smaller than the electric contribution. That what it tells you that electric field, if you play around, it will immediately decohere the system. So you're playing with the magnetic field, magnetic levitation, and people have levitated frogs. Diamagnetic levitation technique is well known. Even in Toronto, Hyvison's group levitates atoms in an atom chip. So similar technology goes into constructing this kind of experiment. So you have to construct a special chip, and this is the chip design. So another aspect of this is how you're going to build your chip design. So millimeter size design, you have to play with it's just a prototype example of the current distribution and the shape of the chip. And that tells you that what you are going to do is that you're going to levitate the diamond. So this is your chip, you're going to levitate the diamond here, and it will have a different potential. The sharp potential is to cool. You need to cool the diamond, and then in the long potential, so in the shallow potential, you're going to create this superposition. And I spoke about your conducting sheet and also the superconducting sheet. So you see that how it plays, because you have your diamond has dielectric properties, it has diamagnetic properties. So you have to take into account of all those interactions. So Casimir-Polder interaction. So you see that how sheet helps you. So just to give some idea about this graph, the green line tells you just about the gravity between the two spheres, two levitated nanodiamonds. The red one is Casimir-Polder, because short distance Casimir-Polder at roughly around micron-sized distances becomes very important. And then you have dipole-dipole interaction. You have got magnetic moment-induced interactions. So you need to overcome those interactions. You see that you are overcoming. So this is one small corridor where at this distances you can see gravity becomes. Because if gravity can entangle, all of the interactions can entangle. So that's the beauty. So before even seeing gravity, people are trying to see whether you can entangle this magnetic moment. Then Casimir, through Casimir you want to entangle, through dipole you want to entangle. So these are the experiments which will be done first before we could reach the gravitational sensitivity.
So just so I understand, the layout here, the idea is that it's horizontal, like the beam passes horizontal parallel to the ground.
You mean the chip?
Yeah.
Actually, it can be done this or this. Either way it can be done. So here, of course, I've shown it horizontally in the sense the gravity is acting like this. But in reality, also you can do the experiment like this. You levitate it.
Yeah, I guess my question was, why not try to do this in free fall? Like then you don't need to let it in.
Very good question. So initially we were thinking about the free fall experiment, but the problem is that in free fall, even if you allow it 1 second, it will fall 5 meters because of the G. And so you need to then have a very good levitation. Your experiment becomes even more expensive because your the vibration isolation becomes even more challenging because keep everything, even forget 5 meter, even 1 meter, 2 meter fall, I cannot tolerate. So that's the reason actually we gave it up and we moved into more space minimizing experiment where we can control it better. The gravity gradient noise or relative acceleration noise becomes much worse in that case. So initially actually our idea was to do free fall, exactly as you said. Okay, so and now comes, you see that sometimes this is the beauty about physics, that whatever you learned in your childhood days, you can still use it. So now I'm using, because I was working on inflation, I'm using some of those techniques to create superposition, which actually when Lev, I wish Lev ahead, and Lev had worked quite a lot in this tachyonic instability, tachyonic preheating, tachyonic inflation, and so on and so forth. He had written many beautiful papers, highly cited works. Some of those ideas we're actually implementing in chip design. So in principle, you can even see the effect of cosmic inflation in your experiment. So the idea is that you have your separated Alice and Bob. You have got this conducting, conductor and superconducting layers, and you have this is the direction you are going, almost like a flat direction. Keep the light flat directions for baryogenesis. But these flat directions where particle can move. It's like a stochastic inflation. If your potential is fairly flat, the particle will jump up and down, up and down. Exactly the same thing is happening here. So you see that here, with the help of Stern-Gerlach, you're separating the spin states, and then through this inverted potential, you're trying to span the wave function. And then through harmonic oscillator, you're trying to bring it back, because you want to do the interference pattern. And eventually, you want to see, you want to interfere at this, there are 5 stages. And all these 5 stages now you have to mimic it, or you have to design your chip in such a way that you can realize it in that direction. Of course, it's tricky, because immediately you would say, what happens? Because of the Maxwell's equation, there will be fluctuation in the y direction, there will be fluctuation in the z directions. So you have to take all those things into account. So a very simple prototype example has been realized with atoms. It has been done by Ron Follman's group in Ben Gurion in Israel. And before the war, so even I have seen this experiment myself. So they took 10⁻⁴ Rubedian atoms, which is mass, each individual mass is 10⁻⁻26 kilogram, and on a chip, exactly like the one which I've shown you, similar kind of design. They have created this superposition, they have closed the interferometer. You see that there's a 50-50 population, and this part illustrates this delta Z difference, where you see slightly different population of spins or your atoms. So a prototype experiment has been done with this by using Stern-Gerlach interferometry. Of course, the mass is very, very tiny, you see, and now you have to push the game something like 10 orders of magnitude. So before I close the talk, there's another ambitious experiment which brings me very close to. Actually, I discussed this possibility with Jonas Strickland last time I visited Canada. This is even more futuristic, because what you are trying to do is that you want to mimic this experiment, the classical experiment of light bending, but now you want to see whether matter and light can be entangled or not. And in principle, again, it can be done, but it requires even harder requirements, just harder requirements. You need a very high intensity beam But such high intensity beams exist with lasers. Many countries, even Canada, France has this kind of facility, but you have to let it go back and forth, back and forth, back and forth. That is hard in laser optics. Laser with high intensity, you can do one-shot experiment. You cannot repeat it because most of the energy goes into waste. That's the problem which actually Donna gave me to, if we could solve it, then we could solve a big problem in laser physics, but unfortunately I'm not an expert. But anyway, this is the level of challenge this experiment has. But the idea is very similar. You create a superposition of matter, roughly 10 kilogram, which actually you can do because LIGO has cooled the 10 kilogram mirror sufficiently close to the ground state. So they can reach maybe, let's say, in 5 years' time, they can create a macroscopic superposition, very tiny macroscopic superposition for a very heavy system. But now if you take a laser beam, and you can perhaps understand this interaction. Now, why this experiment is important? Because of one reason, because this experiment will truly see this tensorial nature of gravity. Because you see the light bending, for the case of Newtonian gravity, there is a prediction which goes as 2m over r. For Einstein's GR, it is twice that of Newton. And there is a theory of some, perhaps many of you might know, due to Nordstrom. He was, I think, Finnish mathematician, and he wanted to simplify general relativity. So his point was that instead of tensorial structure of general relativity, can I not mimic it purely via scalar structure, spin zero? And he was successful in explaining the Newtonian potential with that. But where his theory fails is precisely to explain this light bending. And that's the way, even way back when this experiment was done in 1919, that was a clear indication that how the tensorial structure of gravity comes in to play to predict the light bending in the case of general relativity. So if this experiment can be done, that will be even more beautiful. But of course, it has its own challenges. But in principle, it is possible to do this experiment. So what is the vision we have? You see that we are actually in the bottom. Right now, if you ask what people have achieved, people have created superposition. The biggest the massive case is 10 raised to minus 21 kilogram, roughly micron size, nanometer size, femtometer size separation people have created by Marcus Arndt, Zeilinger's group. Zeilinger got the Nobel Prize. His student was Marcus Arndt. He did this fantastic experiment. But now we want to push this to in first 5 to 6 years. This is the roadmap we have to do for the European Research Council recently. We want to go to heavy system 1 part in 15, and we want to create a very small superposition. Below even, we will go from start from 10 raised to minus 15, and we'll go to nanometer size stuff in first 6 years. And then we push the technology from 6 to 10 to higher, largest spatial superposition, and eventually to maybe 15 years, 20 years time, we will do this. And side by side, we have to, again, ramp up the R&D sector for the gravitational wave isolations, the isolation thing which I have talked. Now, it's really a discovery frontier for us. It's like your LHC experiment. I didn't get time to talk about what it can do, physics beyond the standard model, but now you can just visualize yourselves. If you can take the weakest interaction, which is gravity, if you can probe through this experiment, on your way, you can actually probe any physics which has long distance, consequence. You can probe that. Axion physics, hidden sector, hidden photon mediated interaction, axion mediated interaction. So you can probe this kind of new physics. You can probe even different kinds of gravity, massive gravity, or f of r gravity, or higher curvature gravity. If you get extra degrees of freedom, if you are propagating between your two masses, you can probe those things. So in some sense, it has a huge discovery potential. Maybe you would discover physics beyond the standard model much before you could probe even gravity. And the application side would be the extreme sensor, because gravity is so weak. You're measuring this 1 part in 15 meter per second square in 1 second. If you can measure that if you can sense that kind of acceleration, accelerometer, you are sensing, everything perhaps above 1 part in 9, 1 part in 10, 1 part in 11, 1 part in 12 meters per second. You see that these are extreme sensors in some sense. And I was just curious to look into Canada's national quantum strategy, and I found that there are 5 principal quantum technologies. So there's a huge effort going on in quantum computing, which is fair. We all want quantum computers, but the experiment is even more testing, even more demanding. One place where it doesn't require the rigor of quantum computer is the scalability. You don't require 10 different, Alice and Bobs. So this is the place where quantum computers are much more demanding. We don't require quantum software immediately, but in future maybe it may be useful if you're in the advanced stages of your experiment. Quantum communication depends on your quantum coherence, and you require extreme coherence to do this experiment. So in some sense, they are complementary. Quantum sensors, yeah, as I said, that's the most sensitive quantum sensor we will ever build, perhaps, on Earth. Quantum material, I didn't get much time to get into that. You need the purest qubit, because these are qubits. The dirtiest part is this, because you see that at a nanometer, you have to really play with this quantum material side. You need to clean the system. You need to do many, many things. There are even defects. You have to get rid of them. So this is beneficial for every quantum system you want to create. So with this, let me wrap it up by saying that my interest was actually to do quantum gravity, to understand very simple question. But then it has led me to get into the entire gamut of physics curriculum. You name it. As I said, that even I have to think about the cosmic rays, because it's going to destroy my experiment, laser physics, material science, condensed matter, particle physics, quantum information. And I think that's the beauty of any rich physics. If your physics is rich, it will involve everything, every aspect of your curriculum. And recently, Nature was highlighting one of our works. And yes, it's truly a community effort. So please join us. We have got a small community. It's nowhere as close as LIGO, LISA, or Einstein telescope, and nowhere close to any of the dark matter experiments, as a matter of fact. We are a very, very small group, but please join us. There are many, many open problems here, and it's extremely highly disruptive, ambitious research program. And as a kid, I think we have all watched Scotty Beam Me Up. After all, this is what we are trying to do, of course, for microscopic nanoparticles. So thanks. Thank you very much for your.
We have we're going to go upstairs for some snacking stuff and discussion, but we could have a few questions here in the room.
Hey, so we had many interesting conversations about this. So I'm curious. We both come from particle physics, so my default is that I know how to quantize gravity because quantum field theory at the scales that I can access is stupendously precise and correct with a capital C. So my question is, these alternative things about gravity being quantum, being classical quantum. In my mind, it's hard to even imagine what non-quantum, non-graviton exchange gravity would look like. Is there a consistent, coherent mathematical formulation for the alternative hypothesis that you would detect, and one that's not immediately invalidated by the fact that quantum field theory works at the scales that I can observe?
That's a wonderful question, because actually this has been a debate for almost the past 6 or 7 years. So you're absolutely correct. Even in my mind also, I come from the same background, and I believe that gravity should be quantized. But there is no experiment. So in some sense, there is an impetus to do an experiment. But there are colleagues, trust me, there are many colleagues, maybe next 100 kilometers or 50 kilometers away from us. Also, there are few colleagues who think that gravity is inherently
sorry, I know we're low on time, but I understand testing things is fun and important in science and so on, and I understand that there are quantum gravity people, although they're not what I would call quantum gravity. There is a difference in terminology. We're not talking about string theory here, okay? That like to give colloquia where they say that I couldn't build a Sternberg-like experiment by scattering gravitons off the moon or something like that. Now, my arrogant quantum field theory statement is these guys need to learn quantum field theory because I don't know how to make that consistent with the fact that quantum field theory works for everything else. So is there a consistent version of the alternative hypothesis
I'm arrogant.
by that standard? Yeah.
So far, I have not seen one.
Okay.
You're absolutely correct. But I know there is a colleague of ours who's sitting in UCL. His name is, I forget his name, but he's trying to construct. But of course, there are many, you need to show. If I have huge respect for those people, those no-sayers, because you have to show everything, whatever you have learned so far, that is consistent with classical gravity and not with quantum. It's extremely hard, but there are a few colleagues like that who actually have chosen that path, and they try to push the idea that, yeah, there could be classical interpretation in a stochastic sense, even including in IS Princeton University. Adler had some thoughts. So time to time people do have such thoughts.
Yeah, I understand those constructions have a lot of serious fundamental flaws.
Yeah, they have to show many things.
From your experiment, do I learn anything about what you and I would call quantum gravity, the completion of quantum gravity?
That part. The UV part will not know. We will know only the infrared part. At best, like as I said, that maybe if we can champion this game, maybe 100 years later we can do the H bar, because that's way too small. Maybe extremely sensitive experiment can be built, and that would be fantastic to see the H bar terms. That itself would be a huge struggle. It opens up new corridors. But yeah, maybe someone can say that suppose if you do the experiment, you run 1 billion times, you see no witness. What does it mean? Of course, then the kind of question which you have asked becomes very relevant. What is mean by gravity? Then what is the meaning of space-time? Then it opens up a new Pandora's box. But
sure, that would certainly.
It will definitely, baffle us even more.
I would be baffled, yes.
So, how do you test in your setup that your two nanoparticles are in the quantum superposition?
So your question, how do you
I
enter?
mean, you have this goal of increasing separation and maintaining simple coherence, right? So how do you test that experimentally?
Very good question. Yeah, so the first, in the first 5 years, this is exactly what we have to do. So it's, so before even going to this entanglement experiment, you just measure this simple phase, Colella over Hauser-Werner phase. It's called cow phase due to gravity. This Earth's gravity, you can measure the phase. You can measure the phase because of the Casimir or dipole. So all those things will give you phases, and you, after the interference experiment.
Wait, you've got two particles made out of what?
I'm sorry.
What are the particles made out of?
Oh, these are nanodiamonds.
Nanodiamonds. And then what are you measuring to determine their state?
So the spin. So you're doing the spin of interference. So just one.
Measuring the actual macroscopic rotation.
Exactly. So just one experiment. Let's say the left part. Let's forget even the right part. So you need to characterize all those things. So your question is extremely pertinent. So these are the things we need to do before even bring in the second person.
Okay. And then how do you measure the rotation?
So essentially exactly like the atom interferometer has been done. So this kind of experiment. Yeah. So you look into you do one experiment, one interference experiment, and then you look for populations and see
what are you scattering or interacting with the nanoparticles?
So here is a magnetic field. So it's spin magnetic field. So S dot B interactions becoming important. The induced magnetic B square term becomes important. So you're playing with these kind of terms. You're Hamiltoning.
So these particles have an moment.
Yeah, exactly. So just I may give you an example since you raised this question. Yeah. So this is your.
Some impurity.
This is your. So this is your Hamiltonian, and this is your spin S dot B.
So what's the impurity you're using?
Oh, the nitrogen vacancy. So what happens? Okay, it's a very good question. It brings us to the material science. So if you take a pure diamond, Pure diamond has wonderful properties. It's transparent. You shine light, it doesn't absorb. Now, what absorbs is your defect. So if you have some, if you create a defect, artificially you have to implant it. Sometimes you can get it naturally. Just a naturally occurring diamond, which our people buy, and you see yellow, green, all sorts of, is because of the presence of defect. So the more defect you have, the more colors you see. It's like your aurora borealis. So exactly something similar, like infrared scattering. So anyway, so you want just one defect, or minimize the number of defects as much as possible. And that inside the defect, so there is a vacancy where you embed an electron, so it becomes like your purest qubit. And the purest you make, the better it is for your experiment. And it's a very similar interaction, like just the standard S dot B V square interaction, and then you play around with that.
So then also you talk at the very beginning about quantum versus classical interaction. And there's obviously some background to that where the distinction is being well defined. But can you go further and review for us how that distinction is typically made in this business?
Sure. So you see that in the simplest case, what happens in that you pick up any theory. There are kinematical properties of your theory and the dynamical. Now, kinematical properties, I mean, you can have imposed this uncertainty principle, XPX, and all sorts of things. You can do it even classically in non-commuting theories. Many people play that game as well. So that's one aspect of any theory. The other aspect comes in the interaction, because you want to propagate something from point A to point B. And in that propagation, you can change the property of your system, like spin 2 nature of gravity, or spin 1 or spin 0. And that also determines how your quantum system behaves, the process of interaction. So these two things are combined, gives you the full theory. So in the case of this experiment, we are actually testing the second part, the entanglement, how the interactions can lead to entangle the system. And through that entanglement, we are verifying whether underlying gravity is classical.
I'll ask you some more.
Sure.
Yeah, let's have further questions individually upstairs and the other opportunities in the session. And let's close off this session by thanking you very much for your time.
Thanks.